In 1935, Einstein rolled his eyes at quantum entanglement and dismissed it as nothing more than spooky action at a distance. Fast forward to 2025, and that same spooky effect now sits at the core of experiments in unhackable communication and trials for a future quantum internet. How did something Einstein mocked turn into the foundation of technology shaping tomorrow? And what does it mean for us that particles can stay mysteriously linked across space, no matter the distance? What Einstein once called spooky now protects bank transfers. Here's how. To see why, we need to start with Einstein himself. Einstein versus entanglement, from mockery to legacy. Einstein's uneasy relationship with entanglement began in 1935, when Boris Podolsky and Nada Rosen published what became known as the EPR paradox. In their thought experiment, they argued that quantum mechanics was leaving something out. If the theory were truly complete, it should not allow two particles to remain linked across vast distances in a way that appeared instantaneous. For Einstein, this violated the principle of locality, his conviction that no influence could travel faster than light. He ridiculed the idea with a phrase that would stick: spooky action at a distance. To him, this was not an elegant feature of nature, but a sign that quantum theory was unfinished, a placeholder until hidden rules were discovered. The contrast with his earlier work is revealing. Einstein had already shown the world that time and space were not fixed but flexible, bending under the weight of matter and energy. That was a radical leap, yet to Einstein it maintained coherence. A vast cosmic clock still ticked by rules, just different ones than Newton imagined. Quantum entanglement, however, looked like disorder. It suggested that two particles split apart to opposite ends of the universe. He imagined them as if tied by invisible wires, an unacceptable violation of the logic he had spent his life defending. To him, randomness and non-local influences belonged in mysticism, not physics. Yet his rejection did not stop others from taking entanglement seriously. Erwin Schrödinger, responding to the EPR paper, coined the term entanglement itself. He went further, calling it the defining trait of quantum mechanics, the thing that most clearly separated it from classical ideas. This disagreement set a stage that stretched across decades, Einstein calling entanglement a flaw, Schrödinger declaring it a foundation, and physicists everywhere wondering which of them time would prove correct. The real turning point arrived in the 1960s, when John Bell reframed the debate. Instead of arguing in abstracts, he turned entanglement into a measurable prediction. Bell showed that if particles were only governed by hidden variables, a classical explanation in line with Einstein's realism and locality, then correlations between their outcomes would obey certain restricted patterns, now called Bell's inequalities. But if quantum mechanics were right, the results would break those limits. This was a revolutionary shift. The question could finally be answered not by opinion, but by experiment. One clear example? Prepare two entangled photons, send them to separate detectors, measure their polarizations, and later compare notes. If their correlation went beyond Bell's inequality, quantum mechanics would win. That experiment was first attempted in 1972 by John Clauser and Stuart Friedman using entangled photons. Their setup, though limited by technology, already showed results aligned with quantum predictions. Over the next decade, refinements accumulated. In the early 1980s, Alain Aspect and his team in France ran a series of sophisticated experiments designed to rule out loopholes. Fast-switching polarizers ensured that a decision made on one side of the experiment could not influence the other before the result was registered. Once again, the inequalities fell precisely as quantum mechanics had predicted. It became harder to imagine that classical hidden variables could explain away the correlations. Still, physicists wanted more certainty. Each experimental round raised new questions. Could detectors be missing too many particles? Could subtle communication between systems still play a role? Through the 1990s and 2000s, Anton Zeilinger and others pushed entanglement into new territories. They sent photons through kilometers of optical fibers, bounced signals between telescopes, and even demonstrated entanglement across distances measured in hundreds of kilometers. These bold feats not only tested Bell's framework in increasingly extreme conditions, they also hinted at the practical applications we see being explored today. Then came 2015, when multiple groups in the Netherlands, Austria, and the United States carried out what were called Loophole-Free Bell tests. By combining highly efficient detectors with fast, Space-like separated choices of measurement settings, they closed both the detection loophole and the locality loophole at once. The results were decisive. Bell's inequalities were violated, quantum mechanics was upheld, and Einstein's vision of a hidden local explanation was set aside. Later recognition came in 2022, when the Nobel Prize in Physics went to Aspect, John Clauser, and Anton Zeilinger for proving through decades of experiments that entanglement is real and measurable. The implications of these results reach far beyond resolving a philosophical standoff. When Bell's inequalities were broken in lab after lab, it demonstrated that reality at its most fundamental cannot be accounted for by a collection of independently existing parts obeying straightforward local rules. Instead, particles are bound together by correlations that defy separation. Entanglement means that what happens to one system cannot be fully described without acknowledging another, regardless of distance. Experiments gave flesh to what had once been only mathematics, forcing physics to embrace a connectedness built into nature itself. And where does that leave Einstein? It would be oversimplified to say he was simply wrong. His instinct that entanglement threatened our understanding of reality was absolutely correct, just not in the way he expected. He warned that allowing for these spooky bonds would destabilize the neatness of physics. Experiments later showed that destabilization was unavoidable because it reflected how the universe actually functions. His caution was rooted in consistency, and it is precisely that consistency which his view could not maintain once tested. Rather than undermining his legacy, the story highlights his role as both critic and catalyst. His skepticism forced others to sharpen their theories and build the experiments that proved entanglement true. The irony is difficult to ignore. What Einstein once dismissed has become a validated cornerstone of modern physics. The particle connections he regarded as implausible now support technologies that will transform how information can be processed and shared. They serve not as a quirk, but as a resource, guiding researchers in building communication systems designed for security and performance beyond anything classical physics could allow. The skepticism of one era has become the toolkit of another. This perspective also matters because the story does not stay confined to textbooks or laboratories anymore. From satellites sharing entangled photon pairs over vast distances to quantum keys that secure digital communication, entanglement has begun moving into the structures of daily technology. As experiments keep proving its reliability, engineers are finding ways to turn this strange physical principle into a functional tool. What once seemed to Einstein like disorder is now order of a new kind, one that can be applied to the networks and data systems shaping the future. The journey from Einstein's challenge to modern experiments underscores a remarkable lesson. Nature is often stranger and more interconnected than common sense would suggest. But instead of ending as a curiosity, these experiments have built the foundations of an entirely new technological era. And that transition brings us to a pressing question. If entanglement is no longer just a puzzle for physicists, what promises or risks might unfold as it begins forming the backbone of systems built for the world we live in today? The quantum internet of 2025. What scientists are working toward in 2025 is nothing less than an entirely new type of internet, one that is governed not by clever code or faster processors, but by the rules of quantum mechanics. The current internet connects machines with extraordinary efficiency, yet every transaction and every message still carries a basic vulnerability. Encryption can be broken, servers can be compromised, and digital trust can vanish overnight. A quantum internet aims to address that fragility, not with stronger passwords or layers of software, but with the very physics that underlies nature itself. The first question engineers asked was simple. Could a network itself make intruders visible? In classical communication systems, information can be copied or intercepted without the sender or receiver ever noticing. Quantum systems behave differently. When entangled particles form the channel, any attempt to probe them leaves an unmistakable disturbance. The security, in this case, does not rely on probability or on secrecy of algorithms. It is guaranteed by the physical laws governing the particles. The connection itself becomes a sensor, a tripwire invisible yet inescapable. Consider how such a connection works. A lab prepares pairs of photons whose properties are entangled, meaning the measurement of one instantly reveals information about the other. One photon is kept, the other travels through optical fiber or potentially a satellite link to a distant node. Even when separated by hundreds or thousands of kilometers, the bond persists. If anyone touches the channel, measuring, altering, or trying to copy, the entanglement shifts, signaling intrusion instantly. The communication does not transmit faster than light, but its integrity is absolute because any interference leaves evidence that cannot be erased. Several regions have pursued this approach in different ways. China has built an early lead with satellite experiments, most famously through the MQKD satellite launched in 2016. MQKD demonstrated quantum key distribution across 1,200 kilometers and even managed intercontinental secure exchanges between China and Austria, proving quantum secure signals could be sent well beyond the reach of a single nation's ground network. Europe, through its EuroQCI initiative, is pursuing widespread integration of quantum secure infrastructure that links research centers, government facilities, and eventually civil networks across the continent. The United States has focused on advanced fiber-based testbeds and integrated photonic systems through collaborations between national laboratories, technology companies, and defense agencies. Each region emphasizes a different path: satellite distribution, optical networks, or photonic chips, but all aim at the same landmark: reliable quantum communication infrastructure. Recent demonstrations have underscored just how far this development has come. In one milestone, researchers achieved photonic quantum teleportation between chips over 12.3 kilometers of fiber, showing that entanglement-based transfer of quantum states can work over distances well beyond a laboratory table. In another, space-to-ground quantum key distribution proven by satellites like MQKD revealed that links can cross thousands of kilometers and still maintain high fidelity. These achievements have shifted entanglement from theoretical novelty into a tested resource that can be scaled into real networks. While no single experiment accounts for a complete intercontinental quantum internet, together they show the necessary building blocks: entanglement that survives vast separations, photon transmission through atmosphere and fiber, and repeaters that extend fragile signals further than optical limits alone would allow. The consequences for existing encryption are stark. Classical digital security relies on mathematical puzzles, keys generated through algorithms that with today's hardware would require impractically long times to crack. But this line of defense erodes when quantum computers mature enough to run algorithms capable of breaking standard cryptography. In other words, the very machines built on quantum principles will one day shatter most of the codes guarding financial systems, emails, and medical records. The only way to secure information against that future is to turn those same quantum principles into protection mechanisms. Entanglement, used correctly, can do what no software patch can: enforce secrecy by physics. This shift explains why projects are no longer treated purely as academic curiosities. Entire economies depend on constant secure communication, and leaks cause more than financial losses. They damage public trust and have political consequences. That is why China, Europe, and the United States have invested heavily in parallel efforts. Each wants to shape the architecture of the first quantum internet and avoid dependence on someone else's infrastructure. The incentives are enormous, but the distinction lies not in claiming dominance, but in how each chooses to reach the same goal: satellite constellations, continent-spanning fiber networks, or chip-scale devices woven into existing grids. Building such a network has also forced scientists to overcome technical challenges that yield new spin-offs. Photons must retain coherence while traveling through noisy environments. Detectors must register single particles with extraordinary efficiency, and timing systems must synchronize at levels far beyond conventional internet standards. Solving these problems has created tools that reach beyond security. Quantum links allow distributed sensors with unprecedented precision, clock networks that can measure time with sub-nanosecond accuracy, and even possibilities for astronomical observatories around the globe to combine signals as if acting as one giant telescope. All of these are side effects of solving how to send secure messages through entanglement. What sets the quantum internet apart from all previous forms of communication is its defensive posture. Classical systems can always be broken if an attacker is clever enough. Firewalls, antivirus software, and cryptographic updates are responses in an endless game of defense catching up to offense. A quantum internet changes the premise. Hackers cannot remain invisible. The attempt itself shows up in the altered statistics of measurement results. The very act of trying to copy information warns the participants. That makes the balance of power, so often tilted toward attackers, suddenly shift toward those who wish to safeguard communication. For the first generation growing up with such networks, the perspective may look very different. Security might not feel like a privilege or an optional feature. It could appear instead as a natural standard. Stories about stolen credit card numbers or intercepted private conversations could one day sound like relics of a reckless era when systems left vulnerabilities wide open. In the logic of a quantum internet, privacy is not granted by institutions promising protection. It is inherent in how the connections themselves operate. The full global rollout will still take years, and challenges remain in cost, integration, and scaling. But the principle is already working in experimental networks, satellites, and specialized nodes. The concept that Einstein once doubted has not only survived, it is being engineered into the foundation of information exchange. Physics now guarantees what humans alone have struggled to enforce: secrecy that cannot be faked or bypassed. And that reliability is exactly what lets entanglement protect secrets. Next, how that actually works. Unhackable communication, science fiction turned real. Could communication really exist in a form where any attempt to intercept it is instantly visible? For decades, the answer was no. Encryption was the standard method, and while it provided strong protection, it was never permanent. Over time, computing advances eroded its strength. Every code, no matter how sophisticated, was in principle breakable. That left a lingering problem. As long as secrecy depended purely on mathematics, patient effort or technological leaps would eventually expose it. What was needed was not just harder encryption, but communication that built in detection of eavesdropping from the ground up. That is the central promise of quantum key distribution, often shortened to QKD. It does not rely on puzzles that can be solved. Instead, its protection comes directly from the physics of quantum mechanics. At first glance, QKD looks similar to ordinary encryption. Two parties exchange a shared key they later use to encrypt their messages. What changes everything is how that key is created. Rather than sending digital bits that can be intercepted without leaving a trace, the key is generated with entangled photons. Each photon has measurable properties such as polarization. When a pair of photons is entangled, measuring one instantly tells you about the other. Two parties, often called Alice and Bob, receive streams of these particles and measure them using randomly chosen orientations. Their results line up in a way that classical physics cannot explain. The trick is that if an outsider, traditionally called Eve, tries to enter the process, the delicate correlations fall apart. The eavesdropping reveals itself automatically in the chain statistics. Think of it like a rope stretched taut between 2 points. The moment anyone touches it, the rope snaps and both ends feel the break. To make that practical, imagine two banks trying to set up a secure channel. Each receives entangled photons through a dedicated link. They perform random measurements and then over a classical channel compare parts of their data, but not the full outcomes. If the shared statistics remain within the expected patterns, they can confirm no intrusion occurred and extract a secret key. If an eavesdropper tampered with even a fraction of the photons, the disturbance signals intrusion and the session is discarded. The key is either intact and safe, or it does not exist. There is no hidden middle state. Unlike conventional information, photons cannot be cloned without being changed. A law in quantum physics called the no-cloning theorem makes copying impossible. This is not just theory confined to chalkboards. QKD has moved well beyond laboratory demonstrations. Pilots are operating in real-world settings, though it is far from universal. In 2025, there are working deployments in specialized sectors, international banks, certain government channels, and high-security testbeds connecting research centers. In metropolitan areas, such as Beijing, Vienna, and Geneva, installed fiber loops already carry live QKD traffic alongside conventional data streams. In Canada and Europe, projects like QEYSAT and EuroQCI have tested satellite-based distribution of keys that cross entire regions. China's Mishias satellite extended this further by sending entangled photons across 1,200 kilometers, even proving intercontinental key exchange with ground stations in both China and Austria. Each of these demonstrations shows not only that QKD works, but that it integrates with real infrastructure. Adoption is driven by fields where any breach carries enormous costs. Banks need to secure transactions that flow every second across time zones. Defense networks demand higher confidence than mathematical codes alone can bring. National election authorities face pressure to protect communication against foreign interference, and healthcare systems holding some of the most sensitive data about individuals are testing QKD links to prevent leaks. For all of them, QKD is not yet a replacement for classical encryption, but a complement deployed in limited architectures where guaranteed detection of intrusion is essential. The security effect seems subtle, but its consequences are profound. In a system built on quantum keys, information cannot be silently copied and stored for later decoding. Any attempt to listen in creates noise that flags itself instantly. Security shifts from being a moving target, always under threat of future breakthroughs, to something rooted in the physical laws themselves. For the user, it feels ordinary. Employees log into their systems. They exchange files. Satellites beam photons through the atmosphere. The only difference is that their secret keys now come from particles that behave according to rules Einstein once mocked. That irony is striking. Einstein famously dismissed entanglement as spooky action, thinking it was too strange to build into a complete theory. Yet today, governments and corporations rely on that same spookiness to secure financial records, diplomatic messages, and health databases. What he once regarded as a flaw is now a standard defense mechanism against modern hacking. The idea dismissed as implausible is the very mechanism making tampering practically impossible to hide. It is also important to clarify what QKD is not. It does not let information travel faster than light. The actual messages still move through ordinary cables and satellites. What QKD distributes are unbreakable keys that later secure those messages. Once verified, the keys are combined with conventional encryption protocols. The difference is not speed but certainty. The keys cannot be intercepted without evidence. In effect, QKD creates a lock that fractures if anyone besides the rightful users touches it, a lock backed not by computational difficulty, but by physics itself. This shift reshapes how cybersecurity is designed. Whole industries have been built around detecting hacks after they happen and patching vulnerabilities. QKD reverses that posture. With every key exchange, intrusion shows up immediately as errors in the shared data. Hackers cannot remain hidden for weeks, quietly siphoning information. Every attempt to interfere leaves unmistakable evidence. That changes how banks plan their networks, how governments share classified information between continents, and how scientific collaborations move sensitive experimental data. Each leap forward in communication remade how societies connected. The telegraph carried words faster than ships. The telephone brought voices into everyday life. The internet enabled instant global links. In this new stage, the defining feature is not speed or convenience, but verifiable security. Across cities, quantum channels now join fiber loops. Satellites distribute entangled photons across national borders. Test beds demonstrate what full-scale connections might look like. The concept sounds futuristic, but for those using the pilot systems, it is already mundane. They send files, make calls, and carry out transactions without realizing fragile chains of photons are securing those acts. Picture the moment clearly while hackers continue to probe ordinary servers and prey on weak passwords. The highest value communications sit behind channels where intrusion cannot remain hidden. Financial transfers, medical records, diplomatic cables all move with a safety guaranteed by the quantum state of light itself. Instead of secrecy being a temporary protection eroded over time, secrecy becomes the baseline. Every attempt to tamper leaves behind a record. The system works not by creating perfect invisibility, but by ensuring visible warnings. Spying is no longer a gamble, it is immediately obvious. This is the curious fate of entanglement. Once dismissed, it has become the silent custodian of data flows that underpin the global economy. Invisible keys appear and vanish at the rate of 1 billion photons per second, guarding identities and secrets. The defense is not built by clever codes or hidden tricks, but by the laws that bind the microscopic world. And as we have seen, the same strange link that secures information also powers another frontier, machines that use entanglement not just to protect data, but to compute in ways no classical system ever could. Quantum computers and entanglement's secret power. When researchers turn their attention from secure communication to raw computation, entanglement reveals another dimension of its utility. Quantum computers embody this shift, and their distinguishing feature is not speed alone, but the way entanglement binds qubits into unified systems. Unlike classical machines that step through instructions line by line, Quantum processors derive their power through correlations that spread across particles, allowing calculations to emerge from patterns impossible to separate into independent parts. A useful comparison is between bits and qubits. Classical bits sit firmly as 0 or 1, switching rapidly but still limited to one state at a time. Qubits, however, can hold a combination of those states. Entanglement couples them so that the measurement of one fixes the outcome of another, even across large separations. This coordination makes a group of qubits behave like a single, inseparable fabric. To illustrate, some describe this as parallel realities, but a more grounded explanation is that qubits exist across multiple probabilistic states until a measurement collapses them into one. They do not run every possible computation fully formed, but they exploit interference among potential outcomes so only consistent solutions survive. This quality changes the landscape of what problems can be tackled. In chemistry, for instance, simulating how even a modest-sized molecule behaves overwhelms classical computers because interactions balloon exponentially. Entanglement offers a way to represent all those interactions together rather than one at a time. A complex energy surface can emerge within the relationships of qubits, and solutions that evade ordinary models become within reach. The difference is not about surviving longer calculations, but about redefining the problem space entirely. That representational leap has already been tested in practice.